morning, everybody. Today we are going to finish chapter 1, and what we're going to do is to talk about oblique sections. We have talked about normal stress, which is tension and compression, and shearing stress, which is parallel to a surface. And as you may have thought, it may have crossed your mind, that forces and the surfaces they act upon are not always parallel and perpendicular to each other. So what do we do if the surface is oblique, in other words, not parallel or perpendicular to the force? So we're going to build on our discussion of normal stress and shearing stress and talk about the actual stress on an oblique section. So turning to the document cam, we are going to do a little bit of a drawing and then a little bit of math. Once again, the math here is essentially trigonometry and algebra. So if you are more familiar with those than you are with calculus, you are in luck today. And really in this entire class, we don't do very much calculus. But let's take some sort of a structural member. In this case, it's like a 2x4. And we subject it to an axial load, which we will call P. And this nomenclature is going to be a little bit, not confusing, but we need to be careful with our P. We're talking about this axial load. But in this case, instead of looking at like the normal stress, P over A, what would happen if we had some sort of a splice in this board? For example, this board had been sawed apart at an angle, and we had a glued surface at this angle. Well, what would happen as we pulled on it is we can see, I'm going to redraw this surface that looks something like this. Because we have this force P and P prime acting on it, we can see that the force is not parallel nor perpendicular to this surface. And so what really ends up happening in terms of stress is that we have a normal stress that is perpendicular, or is perpendicular to the surface, directed along the axis that is perpendicular to this splice plane. And we also have a shearing stress, tau, that's directed along that plane. So in other words, there's some state of stress that's going to be directed at some angle from that surface. But instead of looking at the entire stress, we look at the normal stress and the shearing stress. There's two reasons that we do that. One of them is mathematical. In other words, up to this point, we've thought about shearing stress or normal stress as being in a cardinal direction, as being an X, Y, or Z sort of a stress. But really, we're talking now about directing it at this oblique angle. We're talking about directing it along the surface. We talk about normal stress, breaking it out from shearing stress, because some materials do not behave the same in shear as they do in normal stress. So you really want to know the value of the normal stress and the value of the shearing stress, because the material may behave differently in those two types of stress. And the other reason is that normal stress and shearing stress, when we look at them this way, are perpendicular to each other. So in the same way that we use X, Y, and Z coordinates because they're perpendicular to each other, or radial tangential components, or radial transverse or normal tangential components, we're always keeping that orthogonal relationship, because in 2 dimensions completely describes the state of stress. And when it's orthogonal or perpendicular, we don't have to use the law of cosines. We can just use Pythagorean theorem to find the actual overall state of stress. Okay? So it makes the math easier, and it also helps analyze the behavior in the material. All right, so going back to my original drawing, the first thing is, how do we do this analysis? What is tau at some angle, and what is sigma at some angle. Okay? The first thing that we have to do is to define what that angle is. And we define it with these equations from the vertical. So the first thing to note is that theta, the angle that the oblique surface makes with some, that is totally blurred out, with some surface is referenced from vertical. You can reference it from the horizontal. In this case, of course, this angle would be 90 minus theta. If you reference it from vertical, the trigonometric identities will flop in these two equations. So you can do it if you don't remember, if you don't write these things down, but it's better to do it from one or the other. And so since I'm referencing it from vertical, I would suggest you reference it from vertical as well, because then you don't have to transform your equations. All right, well, here is the deal. We call this surface the theta surface. Just to make it more complicated, we call this surface the zero surface. So the first thing you can see is it's very easy to confuse these variables. I would not make this choice, and in the past I've tried to correct this for my esteemed colleagues who are writing the textbook, and it only makes it worse, because then the students can't refer back to their textbook, or they look at their textbook and they have no idea. But do pay attention to the subscripts. We have theta, which means along the oblique surface, and zero or not, which means from the vertical. All right, so basically, if we were looking at this, we can see that if we talk about the area, where do I want to write this? Area of the zero surface, or the perpendicular surface. I was going to see if they use dimensional values here. Just a second. In order to be consistent, once again. They don't. All right, so I'm just going to use height and width, okay? So we can see that A sub 0 is going to be H times W. We can further see that the width onto my A sub theta surface does not change, but my height becomes this length, which is actually going to be the height divided by the cosine of theta. In other words, the length that we experience on the oblique section is the hypotenuse of a triangle that has H as its vertical component. So I can then see that this is equal to HW over cosine theta. And I can say then, from rewriting this equation, that A sub theta is equal to, no, I want to do, excuse me, times the cosine of theta, let's put it that way, is equal to A sub 0. So I have a relationship now between A sub theta and A sub 0. And say A sub theta is equal to A sub 0 over the cosine of theta, or I can say A sub 0 is equal to A sub theta times the cosine of theta. I bet you want to see that, don't you? There we go.
And the question, is that an N that's next to the theta? No,
Here?
down. Oh.
Here?
Yeah.
H,
Got it.
height.
So it's
Yep. So this is my first equation, okay? Now, the next thing that we do is, when we take a look at this force P, we resolve P, or P prime, into a component F that is perpendicular to the oblique surface, and V, which is parallel to the oblique surface. And using this geometry, we can see that F is equal to P times the cosine of theta, F along, I guess I could say this, F sub theta, and that V along that oblique surface is equal to P times the sine of theta. Okay? So now what we have is we have expressions for the F and the A, or the P and the A, or the V and the A. In other words, the force and the perpendicular surface for both a normal stress and a shearing stress. So to finish this off, tau sub theta we know is going to be equal to V sub theta over A sub theta, which is P, the applied load, times the sine of theta over A sub theta, which is A sub 0, divided by the cosine of theta. And rewriting that equation, we get tau sub 0 is equal to P times the sine of theta times the cosine of theta over A sub 0. And this is our working equation for shearing stress on an oblique surface. Now similarly, sigma theta is going to be equal to F sub theta over A sub theta, which is going to be P times the cosine of theta over A sub 0 divided by the cosine of theta, which if I rewrite that is P times the cosine squared of theta over A sub 0. And that's our working equation for normal stress on an oblique surface. Okay, so the big deal about this is now, instead of having to resolve those angles for the force and the area every single time, we have equations that do that for us. So the equation for tau along the surface and sigma along the surface is basically, it's a product of things that we can measure. The angle between the oblique surface and the vertical, the dimensions of that area, in this case height times width. It could be a circle, so it could be, pi r squared or whatever, and then times that applied load P. Right? So how do we use this in the last 5 minutes of class? Well, the only thing that we really need to do is to look at these equations and then make sure that you are referencing theta from the vertical. If you're referencing it from the horizontal, you need to subtract it from 90, and then you can do the problems. So having said that, let's take a look at a problem from the textbook. So I'll do one, and then you guys can do one. Doesn't that sound like fun?
This one we just do Monday, right?
If it'll be, I would like you to have it done Monday in case you have questions, but the actual homework set for chapter 1, I think I won't collect until Wednesday. Okay, so I'm going to do problem 129 in your textbook. And then I'll assign you either 1 or 2 problems, 30, 31, 32. I'll assign you 1 or 2 of those. Okay? Are my equations? Yes. Okay, so once again, here on problem 129 in your textbook, they have a wooden plank with a uniform rectangular cross-section and a glued scarf splice, which is just this type of a splice. And they know what the p-value is, and they want to determine the normal and shearing stresses on the glued splice. All right, so they've drawn it in an orthogonal view. I'm going to draw it square just because I do a little better that way. So my board looks like this. And we have a load P. And we're told that P and P prime are 11 kilonewtons. Okay. And then my splice looks like this. Now this is a little deceptive, but I'm told that this angle is 45 degrees. Technically, this is the angle with the horizontal. So if it was 40 degrees, I wouldn't use 40 degrees in my equation, would I? I would use 90 minus 40, because this angle is made with the horizontal, not with the vertical. So just to make a point of that, so you have this in your note, I'm going to say theta equals 90 minus 45 degrees, which is still 45 degrees. So in terms of the number, it's the same, but this is the angle that I want to be my theta. Just happens to be the same in this case. Okay, so my area, my A sub 0, is just the height times the width because it's a rectangle, which is 150 millimeters times 75 millimeters. I'm going to change that into meters, 0.15 meters times 0.075 meters, because that will come out in something per meter squared, which is a unit of a Pascal or some multiple of a Pascal. So if I take 0.15 and I multiply that by 0.75, I get a value of 0.1125 meters squared. All right. So now I can say tau sub 0, or tau sub theta, pardon me, is equal to P times the sine of theta times the cosine of theta over A sub 0. My P value is 11 kilonewtons times the sine of 45 times the cosine of 45 divided by my A sub 0, which is 0.1125 meters squared. And my sigma 0 then is equal to P times the cosine squared of theta over A sub 0, which is 11 kilonewtons times the cosine squared of 45 degrees divided by the area sub 0, 1125 meters squared. Okay. Now, there's another thing here. When you have your calculator set, when you're doing this, first of all, make sure that you're turned not in radians, but you're in degrees, because otherwise your numbers will come out to be strange. The other thing is the cosine of 45 and the sine of 45 are the same number, right? So that's just a peculiarity of this particular problem. Finally, we can see what our units will be. We have kilonewtons per meter squared. That is a kilopascal, or kPa. Okay, so let me see. Let me get rid of this. 45 sine. 45 sine, there you go, is 0.707. 45 cosine is also 0.707. Okay, so 0.707 squared .4999 or 0.5. Okay, so this value is 11 times 0.5 divided by 0.1125 kilopascals. That's my tau sub theta. And my sigma sub theta is same thing, 11 times 0.5 divided by 0.1125 kPa. Now, sigma we have a sign convention for. If its in tension is positive, if it's in compression it's negative, so this is positive. We do not have a sign convention for sigma or for tau at this point. We will, and I'll introduce that later on, but right now it's tau just spins it one way or the other. It's not a fundamentally different physical property like tension and compression. So we'll talk about that in a little bit. So if I take that, multiply it by 11, and divide it by 0.1125, I get a value of 48.8. So tau sub theta, or 48.9, pardon me, 48.9 kPa, and sigma sub theta is positive 48.9 kPa. If we're in compression, it would be a negative value. Okay, now there's two things that I would like you to see here. If you go back to the, first of all, you can see tau sub theta and sigma sub theta have the same value when the angle is 45 degrees. Yes?
Is the sigma kilopascal or hectopascal?
Kilopascals. Yeah, thank you. Let me double check. Yep. Just my bad handwriting. There we go. All right. So, this is a fundamental identity, is that at an angle of 45 degrees, when you have an axial, we have a load that's 45 degrees from an oblique surface, the shearing stress will have the same value as the normal stress. Okay. Also turns out that's the maximum value of shearing stress. Shearing stress is maximum when the force is, it's a maximum when it's parallel, but on an oblique, forget what I just said. I'm not even going to talk about that yet. So let's just say they're the same at 45 degrees, okay, which kind of makes sense. The other thing is that tau maximizes, if you look at sigma, cosine squared. Cosine squared, cosine is a maximum at 90 degrees, right? Because it's at 90 degrees, the cosine is equal to 1. So this actually maximizes when everything's perpendicular, which makes sense. Because cosine maximum value is 1, therefore there you go. D and A are the same. Here, sine cosine is a little bit different, but to find the maximum tau, you could actually just take the first derivative of that expression and see where it is equal to 0, because you look for that 0, the maximum or minimum. But like I said, just ignore what I said about the 45 degrees. It's still true, but we don't need to talk about that yet. Okay, so does anybody have any questions about the work we've done today? All right, so what I think I would like you to do, I'm bothered by the fact that the angle here is 45 degrees because it eliminates from your notes something that's kind of important. So I think I will have you do I'll have you do 131 and 132 for your homework. And then, okay, and that will finish chapter 1 for us. So on Monday, we'll start talking about chapter 2. But I wanted to bring to your attention, I haven't set a due date for the homework yet, which I'll do on the Moodle page. Let me turn this over to the podium PC. I'll do that later on. But if you look at the button for the homework, I added the second assignment. So it's not, oh, this is the wrong one, I apologize. I'm on the first homework. Homework for chapter 1 is homework number 2, which is right here. Okay, so if you look at the content underneath this, we have from lecture number 7, from lecture number 8, and today from lecture number 9. Do problems 131 and 1.32. So those 1, 2, 3, 4, 5, 6, 7 problems are the entirety of this homework set. Okay? So I will post the due date. I would like you to have them done on Monday so that we can talk about them and so that we can move on to chapter 2. But I won't have them due until Wednesday. Okay? All right, do you guys have any questions for me? All right.